Let us now discuss the growth of current in RL circuit. This is a circuit in which a resistance is connected in series with an inductor across a battery along with a switch. Say here, if at t equals to 0 we close down the switch, battery will supply a current I through the circuit. And as I increases, here we can say an EMF is induced in it such that its polarity will oppose the increase in current. So in this situation, if a current I is flowing, EMF induced across the inductor we can write as L di by dt, which we already studied. Now in this situation, if we write Kvl equation for this loop, here we can directly write it as from negative terminal of battery if we will start, it will be plus E, EMF will be the increase in potential difference from negative to positive terminal, then it is minus IR, it is minus L di by dt, which should be equals to 0 in the closed loop, as according to Kvl equation total potential drop is 0. Here we can write di by dt on simplifying, this is E minus IR by L. And further we can write di by E minus IR is equals to dt by L. Now if we integrate this expression, then at t equal to 0 the current in the circuit was 0 and at time t the current rises to I. Now in this situation if we integrate it, this will be minus 1 by R ln of E minus IR, and on the other side it will be t by L. And here the limits of integration will substitute from 0 to I. Then on integrating, this will give us ln of E minus IR by E, which is equals to minus of RT by L. Further, after solving it for the current, we are getting the result to be E by R, 1 minus e to power minus RT by L. This is the value of current we are getting in the circuit, which is growing as a function of time. There is an exponential growth. We can also plot the variation curve of current with time, and some of its characteristics we can study. Let's continue on the next sheet. So in continuation, we have just seen that the current growing in LR circuit is given by E by R 1 minus e to power minus RT by L. We just plot the variation of this current with time. Here we can see that at t equals to 0, initially the value of current here we are getting is 0, and with time exponentially it is growing, and it is growing in such a way that after a very long time the current is asymptotically reaching the value E by R. So here we can say after a long time it becomes a constant value, which is E by R. Here if we just have a look on the circuit where one inductor and resistance are connected in series, then finally the current in the circuit will approach to the value E by R. And when this will become constant, this inductor will start behaving like a straight wire, or it will be of no effect here, because when current is constant, inductor will not play any role. It is of use only when current is changing. Now in this expression also, I think many of you might be finding it a familiar expression which we have studied in case of a series RC circuit which we have studied for charging of capacitor with time. There also we have studied the concept of time constant. Here also we can define time constant of circuit, time constant of RL circuit, which can be written as tau, and this equals to L by R seconds. And here we can see at time is equals to L by R, the value of current is approaching to E by R, 1 minus 1 by E, which is 0.63 times E by R. And here you can see in graph also at t is equals to L by R, the value of current will be raised to 0.63 E by R. That means current is raised up to 63% of the steady state value or the final current. Here we can write at time approximately 5 times the time constant it will approach to almost the full value, or it is approximately 98-99% of the final value, beyond which even up to infinite time not much variation is there. So this is the time after which we can say the inductor is in a steady state. And before this time, the current in the inductor was changing. So this duration is called transient period for growth of current in an inductor. Here for this transient period, we can simply state in the beginning current was 0, and after transient period it will approximately become constant at E by R. So this current E by R is also called steady state current for an LR circuit which is charged or in which the current is grown by a battery of EMF E. Here one more important thing we can see in this expression, that at t is equals to 0, or if we talk about initial moment, then at the initial moment we can see the value of current we are getting is 0. That means if there is an inductor, then at t equals to 0 or at the initial moment, it behaves like an open circuit, or it does not allow any current to flow through it. And if we talk about at t tending to infinity, or if we talk about the situation in a steady state, then here we can see in a steady state the value of current approaches to E by R. That means in a steady state an inductor behaves like a short circuit, or it behaves like a straight wire because current has now become a constant value. You can also recall we have analyzed RC circuit at initial moment and in a steady state, and we found that in the initial moment a capacitor behaved like a short circuit, and in a steady state a capacitor behaved like an open circuit, whereas in case of an inductor the behavior is opposite. So you must be careful about these relations and behavior of inductor in initial moment and steady state, because in coming different kind of problems we are going to use these concepts.